Okay, advanced algebra. Today we're going to move on to our next section that involves graphing the sine and cosine functions. There's a lot of different ways to graph these different functions, and ultimately we're going to be graphing the cosecant, secant, tangent, and cotangent. But if there's only a couple things you can take away from this unit, it's that sine and cosine will drive the understanding of all of the other functions. So mastery of these two functions is absolutely critical for this class. What I first would like to start out looking at is the unit circle of the cosine function. So what I'm going to do is I'm just going to draw a quick little circle here, and let's fill that in. Okay, so if we consider, let's call it just the cosine of theta. So you've memorized a lot of different values. Let me go ahead and put the xy axis on our unit circle. Now if you think of angle measures of theta as we go around our unit circle, what we could put on here is we know that the cosine of 0 radians is 1, and the cosine of let's go up to 90 degrees, so pi over 2, that's going to be 0. And over on the left-hand side, the cosine of pi happens to be -1, and the cosine of 3 pi over 2 is 0. Now, if we wanted to get a couple more values, we definitely could, okay? We could go after, let's just do the 45-degree angles as well. You know that, obviously, cosine is positive in quadrant 1 and 4 and negative in 2 and 3. So up here at a 45-degree angle, which would be approximately right there, we know that cosine is root 2 over 2. It has the same value over here in quadrant 2, except that it's negative root 2 over 2. Consequently, it's also negative root 2 over 2 down here and root 2 over 2 over here. Now, don't forget, the cosine is actually the length of, if, for instance, if I drew a right triangle in here, it's the length of this side right here. So you would say a 45-degree angle is actually its leg that is sitting on the x-axis has a length, an exact length of root 2 over 2. Let me back up and get rid of that on our graph so we don't dirty it up. Okay, so we're going to use this information as always, and we're going to use this to create a table of values to get a feel for what the graph of the cosine function would look like. So let's start out by creating an XY table. And I guess even before that, I should tell you that the function that we are going to be considering is y equals the cosine of x. So this is a little bit different because we're used to using thetas. In this case, x is our input, it's the domain, which will be an angular value, and it will have an output, which is y, which will be one of the values that we've come up with on our unit circle. Now, let me slightly digress and talk about, there are an infinite number of values going around this unit circle. You've memorized those for denominators of 3, such as pi over 3 and pi over 4 and pi over 6, as well as the 90-degree angle measures. We are going to be primarily looking at the ones that are on the x and y axis that give us outputs of 0, -1, or 1. Okay? But let's go through the process here. So if I asked you, if we have an input of 0, what's happening here is you're thinking, all right, well, 0 gets plugged in over here to the cosine function, and the cosine of 0, yeah, it's 1. So that created the coordinate 0, 1. Let's go ahead and get a graph. We'll plot these things as we go. So what I'm drawing now is an XY axis. Okay? I'm going to go ahead and put a handful of tick marks on here. You can as well in your notes. We're just going to get a rough estimation. So I split that in half. I'm going to split each of those increments in a half. And, I have a little more knowledge on this than you, so I know that 2 pi is going to be over here, pi will be here, pi over 2, and 3 pi over 2. And we need some labeling on our x-axis. So how about I make this go to -1, and this will go to +1, and that should get us started. Okay, so the next value that I would consider plugging in, let's say I wanted pi over 2. So again, I'm considering taking pi over 2, and you may be asking, how the heck does he know to plug pi over 2 in? I'm going to explain where that comes from in a second, okay? Once we see the graph, you'll see why those values are important. So I consider taking pi over 2 and I plug it into the cosine of x. Clearly, the cosine of pi over 2 is 0, okay? And then my next logical one to plug in, again, I'm going from here to here, would be the pi. So if I consider the input of pi, if I plug pi into the cosine function, we know that the cosine of pi is actually -1. And then my next quadrant, or excuse me, my next angular measurement would be 3 pi over 2. If I plug 3 pi over 2 into the function cosine of x, clearly we end up with 0. Again, keep in mind, cosine is the value of the horizontal component, or the horizontal leg on our unit circle. And then finally we have 2 pi. If I plug 2 pi in there, I'm again going to get 1 because we know that this function is cyclic. It will repeat itself. Now if I continue to round, obviously at this angle right up here, the next time around it would actually be 5 pi over 2. So I could extend this graph and just go slightly farther and say, well, what if I plug 5 pi over 2 in there? Well, let's see, the cosine of 5 pi over 2, that's at 90 degrees, it's again 0. Now, if you step back for a second, you start to see that there is a definite pattern on the y values, all right? And that's because the cosine and sine functions are both cyclic functions. They repeat themselves because you can only, once you go around the circle, you're getting the same types of outputs. Now, if we go through and we graph these values, so the first coordinate would be 0, 1. So I'm going to graph that. And then if I graph pi over 2, 0, and then I graph 3 pi over 2, excuse me, I skipped one, pi, -1. And then I graph 3 pi over 2, 0, and then 2 pi, 1. And what we have is, if you were to connect it, the first, I guess the gut instinct of a student is to connect them and say, oh, it looks like a V. Not exactly. If we were to take and we went after these intermediate values, which would be root 2 over 2 and -√2 over 2, you would notice that it doesn't land directly in line right here, okay? So we do not want that. What actually is going to happen, and we'll see this in more detail, is that there's a smooth transition between the two, and that it's actually going to look kind of like a hill. It's going to come down, swing across, come up here, and then go back down. So, and we'll put arrowheads on the end, because it would continue to repeat. If we added that other one, I said that 5 pi over 2 would occur over here. It's going to have a value of 0, and so it would continue through. And this cyclic pattern would continue. Now, let's talk about some vocabulary words while we're looking at the cosine function. Probably the first thing that we should be aware of is the fact that it takes a minimum of 5 points to graph our trig function. That's going to happen here, 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 and here. So when you reference your notes from your packet, it may say establish the 5 minimum points. That's what they're referencing. The second thing is the word amplitude. What is amplitude? Well, amplitude is only applied to the sine and the cosine function. And what amplitude is, it's the distance from a peak to the equilibrium of the graph. It should be the same exact distance from the equilibrium to what I call a trough. That should be on 1 right there, not on the one box below it. Okay? So the amplitude of the plain old cosine function is 1. So it's the height from equilibrium. The way I often explain this to students is, anyone that's ever been in the ocean, you know that when waves come up onto the shore, when you're out in the water, you get hit with those waves and you essentially bob up and down in the water as you ride the wave, or you go between the low spot and the high spot in the wave. When I talk about the equilibrium of the wave, that would be as if I could calm the entire ocean. If I could calm the entire ocean, it would lay flat. And if it laid flat, it would be at a height that in our picture here would be at the x-axis. So that's the equilibrium of our graph. All right? So amplitude is the height from a trough to equilibrium, or the equilibrium to a peak. The next one is the period of a graph. Now, this is worth memorizing. The period of the graph is essentially the distance on the x-axis that it takes to complete one cycle. So we notice that if we start from right here, if we ride this graph, when do I get back to that same output? Well, at 2 pi. So if I consider the distance that it takes to go from there to there, we'd say, well, if you start at 0 and you go to 2 pi, that distance is 2 pi. So in general, the basic period of a cosine function, unmanipulated, and we call this the parent function when it has no other numbers in it, just y equals cosine x, is going to be 2 pi. All right, and we will come up with a tactic later for finding those values when we have, per se, coefficients in front and so forth. But the period is the distance on the x-axis that it takes to complete one cycle. For sine and cosine, the general parent one, it will always be 2 pi. The other two things that you should be aware of are the concepts of domain and range. I've used those quite a bit already in today's lecture. If you consider the domain, those are all possible x values that could be plugged into cosine. Now, if we look at the unit circle over here on the left, we notice that it's never undefined. And so the domain of sine and cosine is all real numbers. I'll say that again. The domain of the cosine and sine function is all real numbers. You can plug anything you want in there and it will give you an output. The range, however, are the values of the y's that we would get. Clearly from our picture, we know that the range of y equals cosine x, it goes from -1 to +1, inclusive. So you use square brackets to include those. So for example, if I said, what is the range of this? You would say, well, it's from -1 to +1. If I'd asked you what is the domain of this, you could say -infinity to +infinity, or you could also say all real numbers, which is what that symbol represents right there. Now, the sine function is very similar. We're not going to go into this amount of detail in drawing the sine function, but I do want to show you a very quick sketch of what it would generally look like. So, for your notes, let's go ahead and say, consider y equals the sine of x. So if we consider y equals the sine of x, I'm not going to bore you with going through a table of values or showing you the unit circle, but why don't we instead, let's just draw an xy axis here. Now we know, or I've already said, that the sine function typically completes one cycle, or its period is equal to 2 pi. So I know that it's going to start at 0, and it's going to finish the cycle at 2 pi. So I'm going to write 2 pi over here. Now what I typically tell students to do is, we know that we need 5 points, which means we need to split this in half twice. So what I do is I eyeball the middle, and I can tell that it's going to be somewhere right about there, and I put a tick mark on there. And then I think about splitting in each of those subintervals again. And so I'm going to split it here, and I'm going to split it here. And our eyeball is usually pretty good at doing that. Now, what I want you to do is think about what is between 0 and 2 pi. You know, sometimes it's easier to consider just the coefficient, like the coefficient 2. So I consider 2, half of 2 is going to be 1, so that's talking about 1 pi. And what's in between 0 and pi? Well, of course, it's pi over 2. And then what's between 1 and 2? You know, an easy way to think of this would be to consider this 2 pi over 2, and this is 4 pi over 2, which means that this should be 3 pi over 2. Now, let's crank out some values for our sine function. So very easily, if we're looking at this, if I say, well, what is the sine of 0? Hopefully you've done your homework and you memorized those in the previous unit, and you'd say, well, no, the sine of 0 is 0, so we're going to have a coordinate that's located right here. And if I thought about what is the sine of pi over 2, well, that's going to be +1. Probably should label my y-axis, so let's go ahead and put tick marks here and here as positive 1 and negative 1. So we're going to have a coordinate here. And then you memorize that the sine of pi is 0, and the sine of 3 pi over 2 is negative 1, and the sine of 2 pi is 0. And you can see that that has finished our cycle. Now the graph looks very much the same as the cosine, with one slight difference. The key to having a nice graph is to feather it in. Don't try to draw it too quickly or it'll turn out sloppy. So I know it comes up here. I'm going to go ahead and turn it around so that the reader clearly knows what they're seeing. And so we have our sine function. That's our graph. It's all the domain is all real, so it does have arrowheads on both. Now what I'm going to do is I want to step back and let's take a look at those two pictures. Why don't you take 30 seconds and look at both of them, and what differences do you notice? What do they have alike? Well, hopefully you're noticing that these pictures are pretty much the same. Now, what I'm going to do is I'm going to pick this thing up, and what I'm going to do is I'm going to bring it over here on top, if this thing will allow me to zoom up. And I want you to notice, my scaling isn't perfect, but they're pretty much the same graph. Now, if I take and I line up my XY axis, we notice that they're the same graph, but they're out of sync. What actually is happening here is they are pi over 2 radians out of sync. So if this is where, again, the purple one is the sine function, if I can take the sine function and I can shift it towards the left, pi over 2 units, they become the same function. So that's one thing I want you to be aware of, is the pictures look very much the same. It's just they have different representations initially. Okay? A lot of similarities. So when I show an example of cosine, I'm ultimately showing an example of sine simultaneously, because we know that the graphs are very, very similar. Okay, I think the next logical thing to do is to step back from the sine and cosine functions, and we're going to quickly consider a different function, hopefully something that you're fairly familiar with. So for this next little step, let's consider the function y equals x squared. Now, I think most people are very familiar with this particular function. It's called a parabola, and if I were to snap out a real quick drawing of this, it would look something like this. Parabola. So we know that we refer to this as the parent function because the parent function y equals x squared, it has no translations left and right. It has no stretch factors either horizontally or vertically. And you memorize several different things. For instance, let's switch to a different color. I'll go to blue for this one. If I take and I add a particular value on, let's say I add 2 onto this, then we realize that this would move up 2 units. It would be the exact same picture, but it would move upward. Now, if we doctor this up a little bit and instead we say y equals x minus 2 quantity squared, what's going to happen here is this is a horizontal translation towards the right 2 units. So you would find the vertex move over to here, and it would be the exact same picture but shifted off to the right. I know my picture isn't perfectly scaled, but I think you see the general idea. Now if we back that up again and I instead give you something like, let's say 2x squared, what happens here is this is actually a vertical stretch. So when I teach this, I like for students to think of this almost as a slope. It's as if the parabola is going to grow twice as fast. So we're going to see the thing grow significantly higher. Okay, so it's almost as if I said, what is the slope of this line right here? You'd say, well, it might be 2 in comparison to what it originally was. If I doctored up this coefficient, let's get rid of that stuff there. If I doctored up this coefficient and I said 1/2 x squared, then we would see a wider parabola. And so those are some of the basic translations. Again, these are shortcuts. We could graph every single parabola, even y equals x squared, in a tabular method. You would pick arbitrary x values, plug them in, and find out what the corresponding y value is. Now, we have shortcut methods, and there are two major ways to graph trigonometric functions. What I showed you earlier on was the method in which we use the table of values, the tabular method, or the numerical method. But there's also a shortcut, and I want you to be aware of it, although I'm not going to, I guess, emphasize that in advanced algebra. There's a time for shortcuts, and that's after you have mastered the graphing of each trigonometric function. However, I want you to be aware of shortcuts with translations. So let's call this translations and manipulations for trigonometric functions. And what I'm going to write here is, let's use the cosine function. I'm going to say y is equal to little a times the cosine square bracket b times parenthesis x minus c plus d. And we should probably say that a, b, c, and d, they're constants. They're elements of the real number system. Okay? So this stuff on the end is just kind of like an FYI. The main idea here is this function y equals a cosine b times x minus c. Notice it's in a factored form in the angle, b times a quantity x minus c. Now let's tackle and label what each and every one of these do. Okay, so we've got an element here. It's going to do something specifically. So what I'd like to do is go to the graph, and what I'm going to do is I'm going to pull up the graph, and why don't we use the cosine of x. And if I graph that, I am in radian mode. Let me adjust my axes just a little bit. Notice I'm looking from negative 2 pi to 2 pi. We know that 2 pi is 2 times 3.14, which is about 6.28. Okay, so don't let the decimals confuse you. Remember, 2 pi really is an irrational number, so it's not going to be a neat-looking decimal. What I'd like to do is, we have this label here, and it tells us what the graph is. So right now we're looking at the cosine of x. Now the first thing that I want to do is, if I take this graph and I'm going to try to just drag it straight up and straight down. I've got one component on there, but notice what seems to be changing the most. All right, I'm getting a little bit of horizontal movement, but basically when I have vertical movement, we notice that that's really our d in our formula. Okay, our d in our formula. I'll go back to the original. So what we saw here was that this d is a vertical translation, or a vertical shift. Now what I'd like to look at is the next component is this c factor. Okay? You're probably familiar with this because we just looked at some of the translations involved with parabolas. So if we take this graph and we shift it left or right, what you notice is the number that's moving the most is that one inside of the parentheses. The other one is just because I can't hold it completely steady. So when we have a horizontal translation, that's the c in our formula. So horizontal translation. Now the next one, and this is kind of weird for most students because we're not used to seeing these graphs, is we have a vertical stretch. I'm going to grab the peak of this thing and I'm going to drag it up. What I'm actually doing here, well, I'm manipulating two at the same time. Let me undo that. So my objective here is I just want to take the amplitude and I want to pull it straight down. There we go. That's a better example of it. Notice that the number that is changing the most, okay, I am sliding a little bit left or right, which changes it, But when I move it up and down, when I increase the amplitude, the coefficient on the front of the cosine, it says 4.18 right now, is much larger. So that coefficient on front of the trig function, it affects the amplitude. Okay, so it is coincidental, just happened to be the letter that I chose, but this affects the amplitude. So changes the amplitude. And then finally, the only letter that we haven't tackled is B here, and this one's kind of weird. This actually, what we call, we say that it's a horizontal stretch, and let's see if I can get it where it's going to work here. Horizontal stretch. I need to grab the trough here and just drag it towards the left. So it stretches the thing out horizontally. Now you notice that I'm accidentally affecting the amplitude a little bit, but I don't mean to. All right. So as I horizontally stretch it, that number is changing. Okay. Now the crazy thing is if I slide it to the left or right, you can see how all of these components change. So let's go back to our original. So in our notes we're going to say that this is a horizontal stretch. Maybe we could say changes the amplitude. Another way of saying that would be on this other one, it's a vertical stretch. All right. Now this other one, the horizontal stretch, it also changes the phase. So you can have a phase shift. If you ever hear that, that's when you shift it left or right. But if you change the phase of it, you're essentially changing the frequency of it. For those that are familiar with physics, that changes the frequency of the sound, if you're talking in terms of sound. So that would be the note that you're actually hearing. Okay, so those are the basic shortcuts. We're not going to use those a ton initially. I want you to go through step by step, but I know a lot of you are very, very sharp, and you're going to pick up on those shortcuts on your own. It's just one of those FYIs. I want you to be aware of it. So now I think the next logical thing is I've cooked up 3 examples where I'd like to show you 4 different types of manipulations and 1 method for doing so. Again, this is not the shortcut method. It's a little bit longer, but the nice thing about it is it will guarantee that you get a nice, accurate graph. So for the first example, example 1, directions accurately graph y equals the cosine of the angle 2x with at least 1 cycle. So it needs to complete at least 1 period so we see an entire picture. Let's switch colors. So what I'm going to do here, let's pull that down just a little bit, is I like to be systematic. The first thing to do is to find out what is the amplitude. So a lot of students want to state that. So the amplitude of this graph, again, I'm looking at the coefficient. That's what affects the amplitude. And we notice that the amplitude is equal to 1. All right? That it's still going to go from -1 to 1 on this particular function. Now the period will be affected in this one. Generally what teachers will tell you to do is they say, well, you take the period, which is normally 2 pi, and you divide by the coefficient that is on the x term. Because the coefficient is 2, we know that the period is actually equal to pi. So what's happening is this thing is being horizontally compressed. You can think of it as a spring, and we're crunching the thing down. Now, what I traditionally do, since I don't want to show this with a shortcut method, is if you're asked these questions, you state those on their own. But if you wanted to graph, and the reason I'm having you go through this process is it's going to prove to be beneficial on cotangent and tan, is we know that the cosine function normally starts at 0 and it terminates at 2 pi. That's when it finishes 1 cycle. So we know that one cycle will occur, and this is how I write it. I literally take this angle. So I'm looking at this entire angular value, which is 2x. And I'm going to say, well, if it normally starts at 0, I'm going to say 0 is equal to 2x. In fact, let's write that in the other way. 2x, that angle must be equal to 0, and it will finish its cycle when 2x is equal to 2 pi. Again, this 0 represents when the function would normally occur. This 2 pi is when it would normally stop. Now, if I isolate the equation, on this one I would divide both sides by 2, which tells me that it's going to start at x equals 0, and it will go until x is equal to pi. And notice that this statement corresponds to our original premise that the period will be pi. The distance between 0 and pi on the number line is one unit, 1 pi. Okay? Now from here what I like to do is come up with a data table. So these two ideas are critical. All right? So I'm going to create an XY table. And I know it's going to start at 0 and it's going to go down to pi. And I'd like for you to think of that as 1 or 1 pi. It has a coefficient of 1. So if I wanted to know what is between 0 and 1, let me give you an analogy here. Let's say I've got a 2x4 and I start measuring at 0 and I know that it's 1 foot. If I want to cut that in half, I would want to take the distance between 0 and 1, which is 1/2. So I know that on my tape measure I'd measure 1/2 foot over and I could mark that line. But if I wanted to cut each of those intervals in half once again, I would have a line right here, and I would consider, well, what's halfway between 0 and 1/2? Well, clearly it's 1/4. Okay? That means that when I cut this one in half, I would have to add another quarter. Now, another way to think of this, instead of writing it as 1/2, you could think of it as 2/4. So clearly, this would go 0/4, 1/4, 2/4, 3/4, 4/4. And there you've got it. Okay? So these numbers aren't too bad, but you might run across occasions where they are a little more challenging. So in the middle, clearly we're going to have pi over 2, right? Because we said 1/2 in my 2x4 analogy. And then in between there is pi over 2, and then, excuse me, not pi over 2, pi over 4. And then down over here, we're going to have 3 pi over 4. Notice that I have 5 points right here. Those are the 5 critical points that I told you that we needed to have in order to have a successful graph. Okay? Now this is the beauty. The beauty now is that we're just going to plug all of these values into our function. We're going to have to deal with some fractions, some mental math, and then our memorized trigonometric functions. So what we're going to do is we're going to think about taking 0 and plugging it in to this function right here. So if I plug 0 in, I get 2 times 0, which is 0. And I've memorized that the cosine of 0 has an output of 1. Okay? Now if I think about the more challenging one, now we've got to do some fractions. Pi over 4. If I plug pi over 4 into the equation, 2 times pi over 4 is 2 pi over 4. But that reduces to pi over 2. So now they're asking, what is the cosine of pi over 2? Well, it's clearly 0. If I consider plugging pi over 2 into our equation, 2 times pi over 2 is pi, and the cosine of pi is -1. We do it again. 3 pi over 4 plugged into this equation gives us 6 pi over 4. That reduces to 3 pi over 2. We've memorized that the cosine of 3 pi over 2 is 0. If I plug pi in, pi times 2 is 2 pi. The cosine of 2 pi is 0. Oh, excuse me, 1. Now, you're probably noticing a pattern here along your y outputs, and that is true. You're going to see a very distinct pattern. You always want to be cautious with just assuming that your y value is going to be another value, because that's how you identify your mistakes. Additionally, as we add more translations, such as moving up and down, it's going to change those numbers and it won't be quite as clear. So I want you to bear with me. We definitely are establishing a pattern right now. So the next thing up is, how would you construct this graph? So I would draw an XY axis. Okay? Let's make that a little bit more accurate. And I would prefer that you use a straight edge when it comes to this class. I can't really use a straight edge with what I have right now, but so if we want to graph this, I know I need to go out to 2 pi, so I start by labeling that. And I could count the tick marks on the graph paper, but for time's sake, I'm not going to do that. If I cut this in half, and then I'm going to need to cut it in half once again, now I have my 5 locations. So I know that this would be pi, this would be pi over 2, this would be 3 pi over 2. Oh, I messed it up. I'm using the incorrect values. Sorry about that. If you take a look, so what we want to do now is, now that we have those tick marks, is we need to put our corresponding x values on the x-axis. So our farthest away in our cycle was pi, and in between that we had pi over 2, here we had pi over 4, here we had 3 pi over 4. We need to label our y-axis. I'm going to call this 1, and I'm going to call this -1, and let me get a color to graph with. Now it's just a matter of cranking out our y values. So if we plot 0, 1, I end up with a coordinate here. Looking at this coordinate, pi over 4, 0 lands me right there. Obviously I'm going to be right here on this one, up here, and then, yeah, we finished the cycle in the same location, and we're ready to neatly draw the graph. Now you know what the picture should look like. That's what we opened up with on the lecture today, so we know it's going to be a smooth transition. I like to feather it in. Those that have been in art class, you know what I mean by feathering. There are smooth transitions between the two. So it's going to look something like this. And there you have it, ladies and gentlemen. That's the cosine of 2x. You could graph it in your graphing calculator if you're in radian mode, and you'll be able to come up with that graph. Let's look at another version. Excuse me, another example. So example number 2. And we'll leave the directions out, and we're going to speed this process up just a little bit. So example 2. I'd like to graph y equals -3 times the sine of x. We first are going to start out, we should have an idea of what the picture should look like. The amplitude, because it is a sine graph, is equal to 3. I know I didn't mention this before, but it's always a positive value. The negative sign is actually going to reflect it over the x-axis. So that's something you could add to your notes. Maybe it's worth going back up. On this general form, you could put a note to self. Okay? If it's negative, then it's going to be a reflection over the x-axis. Now, continuing with this example 2, we know the amplitude is 3. The period is going to be unchanged on this one. The period is still going to be equal to 2 pi because the coefficient on the x is 1. Dividing that by 1 isn't going to do much, so I'm just going to put that in curly brackets. We're kind of done with that. This one does not have a phase shift or a horizontal or vertical translation, so it's pretty straightforward. Let's see what this picture is going to look like. If I use the table of values, what it's going to turn out to be here is I've got an x and a y. So I know that it's going to start when 0 is equal to x, or when x is equal to 0, and then it will terminate when x is equal to 2 pi. That's going to be the one cycle that we showed before. There isn't much arithmetic to do with this particular one. Let me emphasize again, there are faster ways to do this, but we're establishing a method for more difficult graphings. So I know that I have 0, and it's going to terminate at 2 pi. I can visualize it. What is between 0 and 2? Well, it's 1 pi. And then what's between that? Pi over 2, and then this would be 3 pi over 2. Now here's the beauty of it. You think you know what the outputs are, but let's go through the process. If we plug 0 in, if we plug 0 into this function, the sine of 0 is 0. If we multiply it by -3, that's still going to give us the coordinate 0, 0. If I think about taking pi over 2 and plugging it in, The sine of pi over 2 is 1. 1 times negative 3 is negative 3. The sine of 0 is 0, so clearly we end up with 0. If I plug 3 pi over 2, I know that 3 pi over 2, the sine of 3 pi over 2 is negative 1. Negative 1 times negative 3 gives us positive 3. And finally, the sine of 2 pi is 0, and 0 times negative 3 still produces 0. Have our 5 quick and easy coordinates. So let's go ahead and get our graph going. I look at this, I know I start at 0 and go to 2 pi, so I'm going to put 2 pi over here, which means pi is going to be right there, and so forth. Now this one's a little more interesting. You always have to keep in mind the scaling on your x and y axis. If this is 1, this is 2, this is 3. Negative 1, negative 2, negative 3. Okay, now we're ready to graph this thing. So if we quickly knock out these points, I have 0, 0, then pi over 2, negative 3, and then pi, and then I have the corresponding coordinate here, and then here. And so if I quickly get a sketch of this, our graph is going to look something like that. This could be a little bit smoother. That's generally speaking what we're going to see. Now, one thing I want you to consider is that this would look, how this would compare with just y equals. So let's say compare with y equals just the sine of x. So the green one is the graph of negative 3 sine x, but how does this compare if we overlaid it on this particular graph? Well, you know that this coordinate would be the same, but then it would be up here, then down here, then here, then here. So if I quickly graphed it, it would look something like this if I graphed y equals the sine of x. And you notice there's a huge difference, okay? It's the amplitude that is completely changing that graph. All right, let's move on to our fourth example. So our fourth example that I would like to take a look at is, third example I'd like to take a look at is y equals 2 times the cosine of 4x. We're going to move briskly on this one. Clearly that 4 is going to affect the period and 2 will affect the amplitude. So we have two different things that are changing our function. So we'll use purple for this one. Clearly, so again, we have an amplitude that is equal to 2, and we know that the period is going to be equal to 2 pi divided by 4, which is pi over 2. So this thing is going to be scrunched down. The spring is going to be compressed, and we'll hang on to that. Now, with that being said, we can take, using the process before, we take our angle, which is 4x, and put it equal to 0, and we know that the cycle will terminate when 4x is equal to 2 pi. Isolating each of these equations tells us to start at 0 and to start when x is equal to pi over 2. Again, 2 pi divided by 4 is pi over 2 reduced. This directly allows us to go with our t-table. So I create an xy table. I know it will start at 0 and end at pi over 2. And this is where things get challenging. Sometimes I'll have students create, when fractions get a little more challenging, I'll have them create two different x tables. Because you'll have a reduced one and you'll have a non-reduced one. So what I want you to do, we're going to use the 2x4 analogy. Let me draw my 2x4 over here. And I want you to think about measuring from 0 to 1/2. If I had a board that was 1/2 of a unit long and I wanted 4 equal divisions of it, then wouldn't you say that I really need that 1/2 board, and then I should divide it into 4s? Okay. Well, in order to do that, what is that equivalent to? Well, that's really the same thing as 1/2 times 1/4. That tells us that every increment on our board should be 1/8. So this makes it very, very convenient. So I need to do the subdivisions. This is really 0, and then I'm going to add an 1/8 on it, and then I add another 1/8 onto it, and then I add another 1/8 onto it, and then I add another one. So I notice I have 1/8, 2/8, 3/8, 4/8. And that's this unsimplified version if you choose to write it like that. So this is equivalent to 4 pi over 8. By the way, and then you just tack the pi on there, and then it'll work for you. In between that, obviously we said was 2 pi over 8. This was pi over 8, and then 3 pi over 8. So I want to pause for a second and let that soak in. I know I'm moving very quickly. Now what we can use the second column for, and this makes it easier when you're graphing, is to say, well, let's use this as the reduced version. So obviously your pi over 8 won't reduce, but this one will reduce to pi over 4, and then this one won't reduce either. So now we have our inputs. Now we can start focusing on getting our outputs. So we need to look at the original function here, 2 times the cosine of 4x, and let's crank this out. So it's typically easier to do this with the reduced column. So if I type 0 in, 0 times 4 is 0. The cosine of 0 is 1, and 1 times 2 produces 2. Notice you've got to be pretty swift on your fractions. If I think of pi over 8, if I plug pi over 8, 4 times pi over 8 is 4 pi over 8. That reduces to pi over 2. The cosine of pi over 2 is 0, and 0 times 2 is 0. If I think of plugging pi over 4, 4 times pi over 4 is pi. The cosine of pi is -1, and -1 times 2 is -2. Now you guys are pretty sharp. I'm sure you can see the pattern. This is going to be a 0, and this is going to be a 2. But I encourage you to always plug them in, because that's going to be your double check to see if you made an error. For instance, if I plug pi over 2, 4 times pi over 2 is 2 pi. The cosine of 2 pi is 0, and the cosine of 2 pi is 1, and 1 times 2 produces 2. So we have the coordinates that we need. Let's knock out a real quick graph. So I'll use the black on this again to get my XY axis. I know that I'm going between 0 and pi over 2. So this thing is technically going to be crunched down. So I'm going to we'll make it a little bit shorter on this particular one. Maybe only this long. And let's put pi over 2 halfway in between each of those. Now we're ready to graph. Ooh, we need a scaling for our amplitude. If we graph our first coordinate, 0, 2, we get a coordinate up here and down here. I think you're probably seeing the pattern already. And we can get a real quick graph. One thing to concern yourself with, sometimes I'll have students, they'll take this graph and they'll make it look like it shoots out. Keep in mind that you're trying to get the person that reads your graph to understand the exact behavior. You have to think, if I gave this to an Algebra 1 student, so let's say, would they understand what you're talking about, or could they accurately describe the graph if you put an arrow out here shooting up? No, they would think it would continue to go on. So you want to make sure that you're rounding the curve in the appropriate way. Now it's time to take a look at our fourth example. The fourth example I would like to graph y equals the sine of x minus pi over 2. Now looking at this, you probably noticed that it's a horizontal translation to the right. This is where the real power of shifting left and right comes into play. If we use the method that I showed you earlier, things can go very smoothly, and you'll know if you make a mistake. Let's first state the amplitude. We know the amplitude will be equal to 1, and that the period is still going to be equal to 2 pi. And the period is equal to 2 pi because the coefficient on here is really 1, so it's not being changed. By the way, remember capital T is actually period in physics. We're just using capital P for common sense variables. Now if we try to find out where it begins and ends, we know that one cycle will begin when our angle, which is x minus pi over 2, is equal to 0, and it will terminate when that same angle, x minus pi over 2, is equal to 2 pi. Solving the one on the left is a piece of cake. We're going to simply add pi over 2 to both sides, and you find that it starts at x equals pi over 2. Solving this one can be challenging. The easiest thing that most students would prefer rather than dealing with the fractions is to clear the fractions. We'll multiply the equation by 2, which gives us 2x minus pi is equal to 4 pi. We're then going to add pi to both sides, giving us the equation 2x is equal to 5 pi, and then finally we'll divide everything by 2, so x is equal to 5 pi over 2. So what we've just established is where the function will begin and where the function will end. So we're going to come up with a data table next. This time I'm going to write it off to the right. So we know it will start at pi over 2. We know that it will terminate at 5 pi over 2. Now, many of the times students will struggle finding the midpoint between pi over 2 and 5 pi over 2, but it doesn't need to be difficult, okay? First of all, we know that our period is 2 pi. So if I wanted to add halfway, I would be adding pi onto each interval, okay? Maybe what we should do is think of, again, the 2 by 4 analogy. So I know that the distance of my 2 by 4 is 2 pi. It goes from here to here. So if I cut that in half, then I know the distance from here to here would be pi. And if I cut that in half again, that my distance would be pi over 2 between each of those increments. So really what I'm doing is I'm just adding pi over 2 onto my first unit. And so 1 pi over 2 plus pi over 2 is 2 pi over 2. Okay, I'll tell you what, let's get a second column here, an unreduced one. We'll call this pi over 2, and then we add 5 pi over 2 down here. So rolling back, we wanted to add a pi over 2 onto it, so that gave us 2 pi over 2, and then we got 3 pi over 2, and then 4 pi over 2. And it's always easiest to sometimes reduce these, but not always. I'm going to go ahead and write them all in here. So pi, 3 pi over 2, and 2 pi. We're going to need those for graphing, but it's sometimes cumbersome to deal with them, I guess, when we're plugging them into the function. So let's go after this. Okay, so if I have pi over 2 and I plug that into here, pi over 2 minus pi over 2 is 0. The sine of 0, well, that is 0, so I have an output of 0. Now this is where sometimes having both columns is really useful, because I'm going to be subtracting pi over 2. If I have to think of pi, I don't have a common denominator, it's going to be more difficult. But if I think of plugging 2 pi over 2, so if I have 2 pi over 2's and I take away 1 pi over 2, I should have 1 pi over 2 left. The sine of 1 pi over 2 is 1, so I have an output of 1. 3 pi over 2. If I have 3 pi over 2's and I take away 1 pi over 2, that's 2 pi over 2, which is really pi, and the sine of pi, well, that's 0. You notice how I'm saying this? It's as if I'm talking about pi's. So I have 4 pi over 2's, and I take away 1 pi over 2, that means I have 3 pi over 2's left, and the sine of 3 pi over 2 is -1. And you can guess what that last value is going to be. It's clearly 0 if you plugged it in there. Now we can crank out this graph very, very quickly. But the one thing that you need to be extremely cautious of is the labeling on your x-axis. That's where you will lose points. I'll label that amplitude of 1. And let's put a tick mark here. Now, we're going to need to have a few more tick marks. You don't want to label right away. I think the thing to do is we notice that we're adding by increments of pi over 2. So what I'm going to do is I'll put, this will be 1 pi over 2. This will be 2 pi over 2, which is pi. And next up, let's see, we got a tick mark here. Let's get a couple more tick marks. So this is going to be 3 pi over 2. This is 4 pi over 2, which is really 2 pi. And this is 5 pi over 2. And you could keep going if you wanted. It's unnecessary. And we'll go ahead and graph these real quick. So make sure you don't start at 0. Look at your coordinates. The coordinates are sitting and staring you right in the face. Make sure you graph them correctly. It's pi over 2, 0. And then pi comma 1. 3 pi over 2, 0. And there's the last 2. And you could see from the pattern, I'll let you catch up here, but you can see from the pattern that my next coordinate would be down here. If I had plugged 0 in, the sine of, so if I plugged 0 in, the sine of negative pi over 2, well, yeah, it's -1. And so my graph very easily is going to look like this. And there you have it, ladies and gentlemen. Again, all of these can be done in several fashions. There are shortcut methods, but when stuff gets very difficult, what technique do you fall back on? You fall back on tables of values. This is a function. When I put an input into it, it will give me a very well-defined output.